Welcome, SIGGRAPH. It is my first SIGGRAPH. I'm so excited to be here. I'm so excited to speak to all of you. And I'm so excited to speak to NVIDIA founder and CEO, Jensen Huang.
Welcome to SIGGRAPH, Lauren.
Welcome
to my hood.
You're a regular here.
Hey, everybody.
Huh?
Great to see you guys.
Jensen, it is like 99 degrees outside.
I know, it's freezing in here, isn't it?
I mean,
I don't know, I'm shaking.
leather jacket.
Yeah, it feels good. Looks good too.
All right, so you
I
have
have a brand new one.
Oh, a brand new one?
Yeah.
How many of those do you have?
I don't know, but Lori got me a new one for SIGGRAPH. She said, you're excited about SIGGRAPH, here's a new jacket. Go do a good job.
It looks sharp.
Thank you.
All right. You have a long history with SIGGRAPH. I mean, when you think about the history of this conference, which has been going on since 1974, and you think about the history of NVIDIA from the 1990s onward, where your DNA was really in, computer graphics, helping to make beautiful graphics. What is the significance of NVIDIA being here today, right now, at a conference like SIGGRAPH?
Well, SIGGRAPH used to be about computer graphics. Now it's about computer graphics and generative AI. It's about simulation, it's about generative AI, and we all know that the journey of NVIDIA, which started out in computer graphics, as you said, really brought us here. And so I made a cartoon for you. I made a cartoon for you of our journey.
Did you make it, or did generative AI?
I had it, hang on a second. I had it made. That's what CEOs do. We don't do anything, we just have it be done. Kind of starts something like this. Hey guys, wouldn't it be great if we had a cartoon and it illustrated some of the most important milestones in the computer industry and how it led to NVIDIA and where we are today. And so we illustrate.
And also do it in 3 hours.
And do it in 3 hours, right? And so this cartoon here is really terrific. So these are some of the most important moments in the computer industry. The IBM System 360, of course, the invention of modern computing. The teapot, 1975. The Utah teapot, 1979. Ray tracing. Turner Whitted, one of the great researchers, NVIDIA researcher for a long time. 1986, programmable shading. Of course, most of the animated movies that we see today wouldn't be possible if not for programmable shading, originally done on the Cray supercomputer, led to, and then in 1993, NVIDIA was founded. Chris Curtis and I founded the company. 1995, Windows PC revolutionized the personal computer industry, put a personal computer in every home, every desk. Multimedia PC was invented. 2001, we invented the first programmable shading GPU. And that really drove the vast majority of NVIDIA's journey up to that point. But at the background of everything we were doing was accelerated computing. And we believe that you could create a type of computing model that could augment the general purpose computing so that you can solve problems that normal computers can't. And the application we chose first was computer graphics, and it was probably one of the best decisions we ever made because computer graphics was insanely computationally intensive and remained so for the entire 21 years that NVIDIA has been here, and since the beginning of computer graphics, in fact. It required a Cray supercomputer to render some of the original scenes, so it kind of tells you how computationally intensive it was. And it was also incredibly high volume because we applied computer graphics to an application at the time that wasn't mainstream, 3D graphics video games. The combination of very large volume, very complicated computing problem led to a very large R&D budget for us, which drove the flywheel of our company. That observation we made in 1993 was spot on. And it led us to be able to pioneer the work that we're doing in accelerated computing. We tried it many times. CUDA was, of course, the revolutionary version, but prior to that, we had a computing model we call CG, C for graphics, C on top of GPUs. And so we've been working on accelerated computing for a long time. Promoting and evangelizing CUDA, getting CUDA everywhere, and putting on every single one of our GPUs so that this computing model was compatible with any application that was written for it, irrespective of which generation of our processors. That was a great decision. And one day in 2012, we made our first contact, Star Trek first contact with artificial intelligence. That first contact was AlexNet. It was in 2012, very big moment. We made the observation that AlexNet was an incredible breakthrough in computer vision, but at the core of it, deep learning was deeply profound. That it was a new way of writing software. Instead of engineers given input, imagining what the output was going to be, write algorithms, we now have a computer that, given input and example outputs, would figure out what the program is in the middle. That observation, and that we can use this technique to solve a whole bunch of problems that previously wasn't solvable, was a great observation. And we changed everything in our company to pursue it. From the processor to the systems to the software stack, all the algorithms, NVIDIA Basic Research pivoted towards working on deep learning. By the way, this is a great place for research. As you know, NVIDIA is passionate about SIGGRAPH, and this year we have 20 papers that are at the intersection of generative AI and simulation. And so in 2016, we introduced the first computer we built for deep learning, and we called it DGX-1. And I delivered the first DGX-1 outside of our company. I built it for NVIDIA to build models for self-driving cars and robotics and such, and generative AI for graphics. But somebody saw an example of DGX-1. Elon reached out to me and said, hey, I would love to have one of those for a startup company we're starting. And so I delivered the first one to a company at the time that nobody knew about, called OpenAI. So that was 2016. 2017 was the transformer that revolutionized modern machine learning, modern deep learning. In 2018, right here at SIGGRAPH, we announced RTX, the world's first real-time interactive ray tracing platform, we call it RTX. It was such a big deal that we changed the name of GTX, which everybody referred to our graphics cards as, to RTX. Another shout out for a great researcher. His name is Stephen Parker. Many of you know he's been coming to SIGGRAPH for a long time. He passed this year, and he was one of the core pioneer researchers behind real-time ray tracing. And we miss him dearly. And so, anyways.
And you mentioned last year during your SIGGRAPH keynote that RTX, Ray Tracing Extreme, was one of the big important moments when computer graphics met AI.
That's right.
But that had been happening for a while, actually. So what was so important about RTX in 2018?
Well, RTX in 2018, so you know, we accelerated ray traversal and bounding box detection, and we made it possible to use a parallel processor to accelerate ray tracing. But even then, we were ray tracing at about, one frame every, call it, 10 frames maybe every second, let's say. Maybe 5 frames every second, depending on how many rays we're talking about tracing. And we were doing it at 1080 resolution. Obviously, video games need a lot more than that. Obviously, real-time graphics need more than that.
And so this crowd definitely knows what that means, but for the folks who are watching online, who don't work in this field, I mean, this is basically a way of really manipulating light in computer graphics.
Simulating how light interacts with
true to life, happening in real time.
That's right.
The rendering process used to take a really long time when you were making something.
It used to take a Cray supercomputer to render just a few pixels. And now we have our RTX to accelerate that ray tracing. But it was interactive, it was real time, but it wasn't fast enough to be a video game. And so we realized that we needed a big boost, probably something along the lines of 20x or so, maybe 50x or so boost. And so the team invented DLSS, which basically renders one pixel while it uses AI to infer a whole bunch of other pixels. And so we basically taught an AI that is conditioned on what it saw, and then say fills in the dots for everything else. And now we're able to render fully ray traced, fully path traced simulations at 4K resolution at 300 frames per second, made possible by AI. And so 2018 came along, 2022, as we all know, ChatGPT came out.
And what's that again?
ChatGPT.
Oh,
You know,
okay, yes.
OpenAI's ChatGPT, a revolutionary new capability, AI, and fastest growing service in history. But the two things that I wanted to highlight since ChatGPT, the industry, researchers, many of them in the room, has figured out how to use AI to learn everything, not just words, but to learn the meaning of images and videos and 3D, chemicals, protein, physics, thermal dynamics, fluid dynamics, particle physics. It's figured out the meaning of these, all these different modalities. And since then, not only have we learned it, we can now generate it. And so that's the reason why you could go from text to images, text to 3D, images to text, 3D to text, text to video, so on and so forth, text to proteins, text to chemicals. And so now, generative AI has been made possible. And this is really the revolutionary time that we're in. Just about every industry is going to be affected by this, just based on some of the examples I've already given you, whether it's scientific computing, trying to do a better job predicting the weather with a lot less energy, to augmenting and collaborating with us creators to generate images, or generating virtual scenes for industrial digitalization, and very importantly, robotics, self-driving cars are all going to be transformed by generative AI. And so here we are in this brand new way of doing things. And so let me just very quickly, Lauren, if you look at where we started in the upper left, in 1964, the way that software was programmed, human engineers programming software. Now, we have machines that are learning how to program the software, writing software that no humans can, solving problems that we could barely imagine before. And now, because we have generative AI, a new way of developing software. I don't know if you know, do you know Andre Karpathy? He's a really, really terrific researcher. I met him when he was at Stanford, and he coined the original way of doing software 1.0, machine learning to be software 2.0. And now really we're moving towards software 3.0, because these generative AIs in the future, instead of using machine learning to learn a new AI for every researcher, you'll probably start with pre-trained models, foundation models that are already pre-trained. And the way that we develop software could very, very much be like assembling teams with experts of various AI capabilities, some that are using tools, some that are able to generate special things, and then a general purpose AI that's really good at reasoning, that's connecting this network of AIs together, solving problems like teams solve problems. And so software 3.0 is here.
I've gotten the sense from talking to you recently that you are optimistic that these generative AI tools will become more controllable, more accurate. We all know that there are issues with hallucinations, low quality outputs, that people are using these tools and they're maybe not getting exactly the output that they're hoping for. Meanwhile, they're using a lot of energy, which we're going to talk about. Why are you so optimistic about this? What do you think is pointing us in the direction of this generative AI actually becoming that much more useful and controllable?
Well, the big breakthrough of ChatGPT was reinforcement learning human feedback, which was the way of using humans to produce the right answers, or the best answers, to align the AI on our core values, or align our AI on the skills that we would like it to perform. That's probably just the extraordinary breakthrough that made it possible for them to open ChatGPT for everyone to use. Other breakthroughs have arrived since then. Guardrailing, which which causes the AI to focus its energy or focus its response in a particular domain so that it doesn't wander off and pontificate about all kinds of stuff that you ask it about. It would only focus on the things that it's been trained to do, aligned to perform, and that it has deep knowledge in. The third breakthrough is called retrieval augmented generation, which basically is vectorized or data that has been embedded so that we understand the meaning of that data. And so
it's a more authoritative data set. It goes beyond just the trained data set. It actually pulls from other sources.
That's right. It's
So
not just
supposedly
pre-trained
going
data
to be-
source.
Right.
It's something, for example, it might be all of the articles that you've ever written, all of the papers that you've ever written. And so now it becomes something, an AI that's authoritative on your, and it could be essentially a chatbot of you. So everything that I've ever written or ever said could be vectorized and then created into a semantic database. And then before an AI responds, it would look at your prompt, and it would search the appropriate content from that vector database and then augment it in the generative process.
And you think that that is one of the most important factors?
These three combinations really made it possible for us to do that with text. Now, the thing that's really cool is that we are now starting to figure out how to do that with images.
Visuals.
Right, and SIGGRAPH is really a lot about images and generation. And so if you look at today's generative AI, you could give it a prompt, and it goes into, in this particular case, this is a edified AI model that NVIDIA created. It's a 2D, text to 2D foundation model. It's multimodal. And we partnered with Getty to use their library of data to train an AI model. And so this is a text to 2D image. And
You also created this slide personally, right?
I personally had this slide created. And so, imagine I'm the prompt, and then there's a team that's kind of like a generative AI, and then magically this slide shows up. And so here's a prompt, and this could be a prompt for somebody who owns a brand. It could be a brand of, in this case, Coca-Cola. It could be a car. It could be a luxury product. It could be anything. And so you use the prompt and generate the image. However, as you know, it's hard to control this prompt, and it may hallucinate. It may create it in such a way that it's not exactly what you want. And to fine-tune this using words is really, really hard because, as you know, words is very low dimensionality. It's extremely compressed in its content, but it's very imprecise. And so the ability for us to now control that image is difficult to do. And so we've created a way that allows us to control and align that with more conditioning. And so the way you do that is we create another model. And this model, for example, allows us to text to 3D. On the bottom, it's Edified 3D, one of our foundation models. We've created this AI foundry where partners can come and work with us, and we create the model for them with their data. We invent the model, and they bring their data, and we create a model that they can take with them.
Is it
And so
only using their data?
Only uses their data. So this only uses all of the data that's available on Shutterstock that they have the rights to use to train. And so we now use prompt generated 3D. We put that in Omniverse. Omniverse, as you know, is a place where you could compose data and content from a lot of different modalities. It could be 3D, it could be AI, it could be animation, it could be materials. And so we use Omniverse to compose all of these multimodality data, and now you can control it. You can change the pose, you can change the placement, you can change whatever you like, and then you use that image out of Omniverse to condition the prompt. Okay, so you take what comes out of Omniverse, you now augment it with the prompt. It's a little bit like retrieval augmented generation. This is now 3D augmented generation. Getty, the edified model is multimodal, so it understands the image, understands the prompt, and it uses it in combination to create a new image. So now this is a controlled image. And so this way, we can use generative AI as a collaborator, as a partner to work with us, and we can generate images exactly the way we like it.
How does this translate to the physical world? How does it translate to something like robotics?
Well, we're going to talk about robotics, but one of the things that I would love to show you, and I had this made not by myself, well, I had it made myself. Okay, this is an incredible video, and this is a work that is done by WPP, Shutterstock, working with some of the brand, world-class, world-famous brands that you'll know. Let's run the video. Let's show you.
Build me a table in an empty room, surrounded by chairs, in a busy restaurant. Build me a table with tacos and bowls of salsa in the morning light. Build me a car on an empty road, surrounded by trees. Buy a modern house. Build me a house with hills in the distance and bales of hay in the evening sun. Build me a tree in an empty field. Build me hundreds of them in all directions,
with bushes and vines hanging in between. Build me a giant rainforest with exotic flowers and rays of sunlight.
Isn't that incredible? And so this is what happened. We taught an AI how to speak USD, OpenUSD. And so the girl is speaking to Omniverse. Omniverse generates the USD and use USD search to then find the catalog of 3D objects that it has. It composes the scene using words, and then generative AI uses that augmentation to generate, to condition the generation process. And so therefore, the work that you do could be much, much better controlled. You could even collaborate with people because you can collaborate in Omniverse, and you can collaborate in 3D. It's hard to collaborate in 2D, and so we can collaborate in 3D, augment the generation process.
I imagine a lot of people in this room who aren't just technical, but they're also storytellers.
This is a very technical room.
Storytellers see something like this
There's like 90% PhDs in here.
and think, I'm not even going to ask you to do a raising of your hand, but I'm sure that would be fascinating. So they see something like this, I see something like this, and I think, oh, okay, that's pretty amazing. You are speeding up rendering times. You're creating images out of nothing. There are probably just as many people thinking, what does this mean for my job? Where do you draw the line between this is augmenting and helping people? Where do you see the line being drawn? And this is replacing certain things that humans do.
Well, that's what tools do. We invent tools here. This conference is about inventing technology that ultimately ends up being a tool. And that tool either accelerates our work, collaborates with us so that we can do better work or even bigger work, do work that's impossible before. And so I think what you'll likely see is that generative AI is now going to be more controllable than before. We've been able to do that with using RAGs, retrieval augmented generation, to control text generation better, reducing hallucination. Now we're using Omniverse with generative AI to control generative images better and reduce hallucination. Both of those tools help us be more productive and do things that we otherwise can't do. And so I think for all of the artists in the world, what I would say is jump on this tool, give it a try, imagine the stories that you're going to be able to tell with these tools. And with respect to jobs, I would say that it is very likely all of our jobs are going to be changed.
In what way?
Well, my job's going to change. The way in the future, I'm going to be prompting a whole bunch of AIs. Everybody will have an AI that is an assistant. And so every single company, every single job within the company will have AIs that are assistants to them. Our software programmers, so you know, now have AIs that help them program. All of our software engineers have AIs that help them debug software. We have AIs that help our chip designers design chips. Without AI, Hopper wouldn't be possible. Without AI, Blackwell wouldn't be possible. You know, this week we're sampling. We're sending out engineering samples of Blackwell all over the world.
They're under people's chairs right now. I think if you just look, you get a GPU.
You and I, yeah, you get a GPU. You get a GPU. That's right.
Supply chain.
We all wish.
Yeah.
Yeah. And so none of the work that we do would be possible anymore without generative AI. That's increasingly the case with our IT department helping our employees be more productive. It's increasingly the case with our supply chain team optimizing supply to be as efficient as possible, or our data center team using AI to manage the data center to save as much energy as possible.
You mentioned Omniverse before. That's not new, but the idea that more generative AI would be within the Omniverse, helping people create these simulations or digital twins.
Yeah, that's what we're announcing this week, by the way.
Talk about that.
Omniverse now understands text to USD. It could understand text to, and has a semantic database so that it could do search of all the 3D objects. And that's how that young lady was able to say, fill the scene with a whole bunch of trees, describing how she would like the trees to be organized, and somehow populates it with all these 3D trees. Then when that's done, that 3D scene then goes into a generative AI model, which turns it into a photorealistic model. And if you want the Ford truck to not be augmented, but to use the actual brand ground truth, then it would honor that and keep that in the final scene. So I think if you do that, so one of the things that we talked about is how every single group in the company will have AI assistants, and there's a lot of question lately about whether all this infrastructure that we're building is leading to productive work in companies. I just gave you an example of how generative AI is impossible without NVIDIA's designs would be impossible without generative AI. So we use it to transform the way we work. But we also use it in many examples that I've just shown you in creating new products and new technology that either makes possible ray tracing in real time or Omniverse that we can now imagine and help us create much larger scenes, or our self-driving car work or our robotics work. None of that new capability would be possible without it. And so one of the things that we're announcing here this week is the concept of digital agents, digital AIs that will augment every single job in the company. And so one of the most important use cases that people are discovering is customer service. And every single group, every single company has customer service, every single industry has customer service. And in the future, today it's humans doing customer service, but in the future, my guess is that it's going to be humans still, but AI in the loop. And the benefit of that is that you'll be able to retain the experiences of all the customer service agents that you have and capture that institutional knowledge that you can then run into analytics, that you can then use to create better services for your customers. Just now I showed you a Omniverse augmented generation for images. This is a RAG, this is a retrieval augmented generative AI. And the thing that we're doing is we've created this customer service, basically microservice that sits in the cloud. And it's going to be available, I think, today or tomorrow. And you can come and try it. And we connected to it a digital human front end, basically an I/O. The I/O of an AI that has the ability to speak, make eye contact with you, animate in an empathetic way, You could decide to connect your ChatGPT or your AI to the digital human, or you could connect your digital human to our retrieval augmented generation customer service AI. So however you like to do it, we're a platform company, so irrespective of which piece you would like to use, they're completely open source and you can come and use the pieces that you like. If you would like the incredible digital human rendering technology that we've created for rendering beautiful faces, which requires subsurface scattering with path tracing, this breakthrough is really quite incredible, and it makes it possible for us.
Amazing graphics researchers, welcome to SIGGRAPH 2024.
So it makes it possible to animate using an AI. So you chat with the AI, it generates text, that text then is translated to sound, text to speech. That speech, the sound, then animates the face, and then RTX path tracing does the rendering of the digital human. And so all of this is available for developers to use, and you can decide which parts you would like to use.
How are you thinking about the ethics of something like this? You're unleashing this to developers, to graphics artists, but these are being unleashed into the world. Do you think a chatbot like that, a very human-like visual chatbot, should say that it's a chatbot? Is it so human that people start mistaking it for humans? They're emotionally vulnerable.
It's still pretty robotic, and I think that's not a terrible thing. You know, we're going to be robotic for some time. I think we've made this digital human technology quite realistic, but you and I know it's still a robot, and so I think that's not a horrible way. It is the case that there are many different applications where the human engagement is much more engaging, having a human representation or near human representation than a text box. Maybe somebody needs companion, or healthcare needs to advise somebody who is an outpatient who just got home. Helping elderlies. There's a whole bunch of applications. A tutor, to educate a child. All these different applications are better off having somebody who is much more human and be able to connect with the audience.
That's interesting.
Yeah.
What I hear you talking a lot about today, these are software developments, right? They're relying on your GPUs, but ultimately, this is software. This is NVIDIA going further up the stack. Meanwhile, there are some companies, some folks in the generative AI space who are in software and cloud services, but they're looking to go further down the stack, right? They might be developing their own chips or TPUs that are competitive with what you are doing. How crucial is this software strategy to NVIDIA maintaining its lead and actually fulfilling some of these promises of growth that people are looking at for NVIDIA right now?
Well, we've always been a software company, and even first. And the reason for that is because accelerated computing is not general purpose computing. General purpose computing can take any C program, C++ program, Python, and just run it. And almost everybody's program can be compiled to run effectively. Unfortunately, when you want to accelerate fluid dynamics, you have to understand the algorithms of fluid dynamics so that you could refactor it in such a way that it could be accelerated. And you have to design an accelerator. You have to design a CUDA GPU so that it understands the algorithms so that it could do a good job accelerating it. And the benefit, of course, is that we can, by doing so, by redesigning the whole stack, we can accelerate applications 20, 40, 50 times, 100 times. For example, we just put NVIDIA GPUs in GCP running Pandas, which is the world's leading data science platform. And we accelerated from 50 to 100x over general purpose computing. In the case of deep learning, over the course of the last 10 to 12 years or so, we've accelerated deep learning by 1 million times, which is the reason why it's now possible for us to create these large language models. 1 million times speed up, 1 million times reduction in cost and energy is what made it possible for us to make generative AI possible. But that's by designing a new processor, a new system, Tensor Core GPUs, the NVLink switch fabric, is completely groundbreaking for AI. Of course, the systems itself, the algorithms, the distributed computing libraries we call Megatron that everybody uses, TensorRT, LLM, those are algorithms, and if you don't understand the algorithms, the applications above it, it's really hard to figure out how to design that whole stack.
What is the most important part of NVIDIA's software ecosystem?
Well, every single one of it takes a new library. We call it DSLs, domain-specific library. In generative AI, that DSL is called cuDNN. For SQL processing data frames, it's called cuDF. And so if you're going to SQL, pandas, cuDF is what makes it possible for us to accelerate that. For quantum emulation, it's called cuQuantum. cuFFT, we got a whole bunch of cu's. Computational lithography, which makes it possible for us to help the industry advance the next generation of process technology, called cuLitho. The number of cu's, it goes on and on. Every time we introduce a domain-specific library, it exposes accelerated computing to a new market. And so, as you see, it takes that collaboration, the full stack of the library, the architecture, and the go-to-market and developers and the ecosystems around it to open up a new field. And so it's not just about building the accelerator. You have to build the whole stack.
NVIDIA is dependent on a lot of things going right. Your foray into the future, your innovation depends on a lot of things going right. You have to continue pushing the laws of physics. You do have competitors who are nipping at your heels at all times. We've talked about this, what keeps you up at night. You're also somewhat reliant on the geopolitical stability.
Last night, just so you know, elevation.
Drink some water.
That's what they told
Dry out
me, but
here.
it was too late. By the time I learned